Hello everyone, I am Dr. Jane Ruth. I am now presenting my work on study on vibrational Raman modes and electrical properties of lead-free sodium bismuth titanate, bismuth magnesium zirconate, lead-free piezoelectric ceramics. First, the introduction about the parent compound sodium bismuth titanate. It is a relaxer ferroelectric. It processes the perovskite oxide structure. In perovskite, it is also known as AbO3 structure. The A site is occupied by two different cations, that is bismuth cation and sodium cation. The B site is occupied by titanium atoms and it is an oxide perovskite. It is a promising high temperature perovskite because of its high Curie temperature and it has a high ferroelectric polarization, and so sodium bismuth titanate is considered as a best replacement to PZT. Also, it has a high ability to form solid solutions with the different compounds with fine-tuned properties. Experimental studies on these solid solutions showed that because of the A site disorder, there is an associated lattice dynamical property that is important to understand the relaxer behavior, dielectric property as well as the ferroelectric properties. In order to understand the dielectric properties, Raman spectroscopy is a best tool for the investigation of the dielectric properties in perovskite type oxides. Now we are going to see about the NBT BMZ solid solution. Here the BMZ is a compound that is substituted in NBT in different mole fractions. This composition is synthesized using the solid state reaction method, and the synthesis sampled were polled and the Raman spectra, structural properties and electrical properties are analyzed. This is a non-MBP system. This system is chosen because it exhibited enhanced dielectric properties, ferroelectric properties, piezoelectric properties without any decrease in the Curie temperature, as well as it decreases the coercive field. One of the major disadvantages of this NBT is it has a high coercive field, so that we can't be able to poll the NBT as it requires more than 73 kilovolt per mm. But when we substituted BMZ with this NBT, the coercive field is decreased, so the electrical properties are enhanced. The synthesis and characterization process. For the synthesis of NBT BMZ ceramics, we used highly purified oxides and carbonates. The raw materials or the starting materials which are used are bismuth oxide, titanium oxide, magnesium oxide, zirconium oxide and sodium carbonate. These powders are taken in the stoichiometric ratio and grounded well and calcined at 850 degrees centigrade for 2 hours. Then the calcined powder is binded with PVA binder, that is mixed with PVA binder, pressed into pellets by applying a pressure of 7 tons and then kept it in the furnace. The PVA binder is removed by heating it to 300 degrees centigrade for 2 hours. After that, the temperature is increased to 1160 degrees centigrade for 2 hours for sintering. After sintering, the sintered pellets are taken out after cooling the furnace. Then the surfaces of the sintered pellets are very polished, and the well polished pellets are used for the characterization purpose. Before going for the structural and Raman spectroscopy as well as the electrical properties, the pellets were polled by applying a DC voltage of 6.5 kilovolt per mm for 15 minutes. The Raman spectroscopy is taken using an argon source of wavelength 514 nanometer. This figure shows the powder X-ray diffraction patterns of 1 minus x NBT x BMZ poles. Here the pattern is given for various mole fractions of BMZ. BMZ is substituted up from 0.01 mole fraction to 0.04 mole fraction. From this, here the figure shows that all the peaks were indexed. No unimpurity peaks or unindexed peaks are seen in all the samples. This reveals that all the synthesized samples are phase pure and it retains in single phase. The well splitting of 1 on 1 peak into 1 1 minus 1 and 2 1 on peak to 2 1 minus 1 and the appearance of the superstructure reflection 1 by 2, 3, 1, 1 reveals that it possesses rhombohedral structure with R3C space group. In all the ceramics, the splitting is seen, so it is observed that and it is confirmed that the synthesized pellets are possessing the rhombohedral R3 phase. This figure shows the Raman spectra of the synthesized NBT BMZ pooled ceramics. In the figure, the base graph is of the pure NBT. This is deconvoluted into 9 Lorentzian peaks by the Lorentzian peak fitting. So 9 modes were observed. This 9 modes, the first we can able to divide into 4 regions up to 200, up to 400, then above 400. So this A region belongs to BIO vibrations and NIO vibrations. Then the B region is related to TiO6 octahedral vibrations, and the C region and D region, that means beyond 400, it is related to oxygen phonon frequencies, that means oxygen vibrations. So theoretically we know that there are 9 modes, more than 13 modes are there. We experimentally we can able to observe only 10 or 11 modes. Out of this, ETO1 mode is predicted theoretically, but it is not observed experimentally. But in our study, we can able to observe the ETO1 mode that belongs to BIO vibrations. Now, this figure shows the changes in the Raman spectra of 1-X NBT and X BMZ pooled ceramics. Here we are going to see, we are seeing the normalized intensity of the peaks in the A region as well as the B region. In the A region as well as in the B region, due to the increase in the mole fraction of the BMZ substitution, there is shift in the A region as well as the B region. You can't able to see much deviations in the C region and D region. This measurement of the 1 centimeter to the power minus 1 peak, we can able to see the ETO1 mode due to the well polished surface which reduces the Rayleigh background scattering and the well ordering of Bi and Na ions in the lattice. So in A region, there is a change in the frequency of the vibrations due to substitution, that is because of the polarizability of the substituted cations in the A site. Regarding the B region, we can able to see 2 modes. The frequency range 247 and 281 centimeter to the power minus 1. Here the peak frequencies are increased and the width is also increased by 20 centimeter to the power minus 1. So this is related to not only the lattice change, but also it is due to the subtle change in the geometry of the TiO2 vibrations, rotational vibrations. So out of the 9 modes, the 7 modes we can able to see the shift, that is due to the volume change due to the substitution of BMZ in the NBT lattice. This figure shows the electrical and structural properties. We can able to relate the electrical and structural properties. The left y-axis gives the piezoelectric coefficient, that is D33. The right y-axis we can able to see 4 y-axis. The first is related to the dielectric constant. The second is related to the ferroelectric polarization. And the third and fourth are related to the structural parameters, that is 90 minus alpha, that is known as rhombohedral lattice distortion, and the delta R, which is known as lattice strain. So here from the figure we can able to observe that for x equal to 0.01 mole fraction of BMZ substitution, we can able to get highest D33, highest PR and almost moderate epsilon R, that means dielectric constant. In this case, the structural property, that is rhombohedral lattice distortion and lattice strain, is reduced. So due to the reduction of the rhombohedral lattice distortion as well as the lattice strain, the non-180 degree domain reorientation is enhanced. So we can able to get an enhanced ferroelectric, dielectric as well as the piezoelectric properties. So the conclusion is, From the Raman spectra, we can able to get all the phonon vibrational frequencies related to BiO, NaO, TiO6 and oxygen phonon vibrations. Now, the intensity of the ET1 mode, that is which is assigned to BiO, that is bismuth oxide vibrations, is changed due to the change in the difference in the polarizability of its substituted cations in the A site. Now, shift in the frequency region, the B mode, that is 247 and 286 centimeter to the power minus 1, it is related to the change in the rhombohedral rotational vibrations. The appearance of the Raman vibrational modes ETO1, ETO4 and A1TO4 are the prime factor for the increase in the dielectric response of NBT. From the Raman spectra, we conclude that due to the decrease in the rotational angle and the decrease in the BiO vibrations is accounting for the enhanced dielectric constant and reduction of the coercive field in BM set substituted NBT ceramics. This due to the increase in the dielectric constant, polarization and the reduction of the coercive field reveals that BM set is a best substitution for NBT in order to reduce the coercive field and enhance the other properties, so it can be used for technological device applications. I wish to end this presentation with the words of Pierre Curie. In science, we can expect to accomplish something. Every discovery, however small, is a permanent gain. Thank you for your listening.